Thank you very much for the introduction and the invitation to speak. All right, so, well, I'm very proud of you all for making it in this early morning after the conference dinner. And for reasons that are entirely unrelated to what I just said, I wanted to start nice and slowly. So with sums of two integer squares. This nice theorem of Fermat tells us exactly which integers are sums of two squares. So it's the ones where every maximal prime power divisor is congruent to 3 mod 4. Congruent to 1 mod 4, excuse me. I said I had to start slow. And what we're looking at is extending this to rational numbers. So we're going to look at a family of quadratic equations and when it has solutions. And it's essentially the same proof. It's going to tell us that if we have a positive rational number y, then it's going to be a sum of two rational squares, which is to say this equation is soluble, if and only if the numerator and denominator of y, every maximal prime power divisor is congruent to 1 mod 4. Every bad prime has even exponent in the prime factorization of the numerator and denominator. And in particular, what this whole talk is basically going to be about is this fact here. So this is, most y's are not like this. So we count rational numbers up to a given height by using this naive height function. So the maximum of the absolute value of the numerator and denominator is the height of the rational number. And with respect to this height, 0% of y's satisfy these conditions and are sums of two rational squares. To be precise, it's a proportion 1 on log of the height of the rational numbers, sums of two squares. Okay, so this is all just fun and games. So what am I really talking about? Well, we can actually consider a more general family here. We can let the coefficients be polynomials in several rational numbers. And it's still true that for most values of the parameters, the equation won't be soluble. Except sometimes it is. I mean, there might be some parametric solution where you can plug in you can plug in x0, x1, x2 being some polynomials in the y's, and then there's like a uniformly a solution. If you exclude that case, then 0% of the time there'll be solutions. Okay, so I'm now going to, so I like to do this thing where I warn you when I'm about to erase part of what's on the screen. As a practice round, I'm now going to get rid of this, which hopefully most of you know anyway. Okay. So here's the formal statement, which actually a lot of the conditions aren't really relevant to the way I'm going to formulate things today, so I'm not going to talk about this in tremendous detail. But this is the formal version of what I just said, that if you have a family of quadratic equations, homogeneous quadratic equations in 3 variables, with the coefficients being some polynomials and some rational numbers, and you exclude the case where it's sort of always soluble for trivial reasons, then it's soluble 0% of the time, 0% of the values of the parameters of the coefficients. And in the same way, we can get a similar looking upper bound for the number of values of the parameters for which it's soluble, saving a power of the log of the height. Okay. And this goes even for, there's a version of this even where the equation is something more general than just a conic. And again, the more general version says that except in some sort of fairly natural cases, you can save a power of the logarithm of the height In that sense, 0% of the time is it soluble. Okay. I'm now going to erase this part. I'm going to keep the bare statement of Serre's theorem. Oh, and by the way, so if you want to go back and look at something that I said earlier, the slides are at tiny.cc/green10. Green tent, lowercase, all one word. And you can see all the slides there, and slide number is next to it if you need to know where I am. Okay. So this is the result that I'm here to talk about. So this says that so this is instead of just parametrizing a family of conics by rational numbers, we're going to parameterize by the points of an elliptic curve. So some sparse set of rational numbers. In other words, rather than having a fibration over a projective space, we have a fibration over an elliptic curve. And so under some fairly mild assumptions, which we'll talk about later, the result says that 0% of the time this conic is soluble, where y is the y coordinate of a multiple of a fixed point on the elliptic curve. And this theorem and everything I'm going to talk about today is joint work with Subham Bhakta, Loughran and Masahiro Nakahara. Okay. Yes, and in particular, so there's some we're saving a power of the log of something here. It's not quite the log of the same thing. So before we were looking at conics with coefficients, which are polynomials in some rational numbers y. We save a power of the log of y. And so here we're saving a power of the log of n. N is the multiple of we're taking the first capital N multiples of a fixed point on the elliptic curve. It's saying that 0% of those multiples have this conic be soluble. This is sort of first shot at going beyond something genuinely more complicated than projective space. Okay. So I'm going to clear out this general statement and talk a little more about this theorem. So this involved taking all rational points of height up to a given bound, whereas this says multiples of a fixed point, first capital N multiples of a fixed point. And we do have a version of the theorem which where you're looking at fibers over points of bounded height on an elliptic curve. In some sense, this is the natural thing to do. So here we've got, again, an elliptic curve, and rather than having a fixed point, we're looking at all points of naive height up to b. So capital H is still the same thing that it was before. It's just you write the point in lowest. You write the coordinates of the point in lowest terms, and then this is the maximum for the absolute value of the numerators and denominators. So we look at points on the elliptic curve with naive height going up to some bound b, and we have this conic with one of the coefficients being the y coordinate of that point. So the total number of, so if I delete this condition here, and just look at the total number of points on the elliptic curve of height up to b, it's root log b to the power of the rank. The assumptions of this theorem say the rank has to be 1. Yes, sorry, square root of log to the power of the rank, yes, exactly. Right, so the hypothesis says that the rank is 1. Okay, maybe you can guess roughly why that is, because we're going to use some version of this theorem to prove this theorem, right? So, I mean, this is only adding torsion. We have multiple. This is just saying, well, all points on the elliptic curves are multiples of some fixed generator plus a torsion point. So sort of natural that the rank has to be 1. And again, it says that 0% of these are. So yes, so if I delete the last condition and just count points on the elliptic curve of height up to b, there's going to be about root log b of them. So this again says that 0% of the time is this soluble, but now the saving is really bad. Yes, the saving is this log. So this, one might be wondering, well, how far is this from the truth? And I'll talk about that in a minute. But actually, I'm not going to talk very much about this more general theorem because like I say, this more general theorem is proved using a version of this theorem. So for simplicity's sake, I'm mostly going to talk about this slightly simpler statement with the slightly simpler proof. Right, so we now say goodbye to the statement of Serre's theorem. And yes, so as I was saying, I'll mostly be talking about this theorem at the top. So let's focus on that now. Okay. Right, so I mentioned, natural question, what does one expect? How far is this from the truth? And this is actually, so I've been presenting this as sort of a generalization of the theorem of Fermat, the theorem of Serre. And there's another point of view from which one might look at this kind of question, which is that actually if one asks what the truth ought to be, the answer is rather peculiar from the point of view of point counting. The answer turns out to be, or some of the possible answers, depending on how you interpret the question, turn out to look rather odd. Okay, so let me unpack that statement. So here again is just we take the first capital N multiples of a fixed point on an elliptic curve under some mild assumptions, and 0% of these have this conic be soluble. So what proportion of them ought to have the conic be soluble? Well, we saw right back at the start. I sort of skipped the details, but we saw at the start that a rational number of height h is a sum of two rational squares with probability about 1 on log of the height. So here I say what exactly that means. And this h is so this is again the naive height. The height of the y coordinate is sort of roughly e to the n squared, if we take the nth multiple of the point. And so we might guess that maybe this count looks something like this. So the probability that this conic is soluble, it might be around 1 on the logarithm of this naive height. And if we sum that over little n going up to capital N, this is summing 1 on little n squared, big O of 1. So what this is suggesting is that maybe this quantity is actually finite. Maybe I could drop this capital N and just let n run over all the natural numbers, and this is just some finite number depending on E and P. Okay, well, I said that was unusual. There are lots of finite quantities in number theory. Well, the thing is, let's look at it this way. So let's write x and y as rational numbers in lowest terms. So because the Weierstrass equation of this elliptic curve has integral coefficients, and I wrote down a few slides ago what exactly I meant by integral Weierstrass equation. We'll see it again in a bit, I believe. So because it has integer coefficients, in lowest terms it looks like this. The denominator of the x-coordinate and the y-coordinate is the square and the cube of some e, which is co-prime to both the numerators. and I've normalized it so that this E has to be positive. So these U and V, they could be negative, but E has to be positive. And I've suppressed the dependence on the point P here, incidentally, which may get confusing later, so look out for that. So U, V, and E depend implicitly on the choice of a point P and explicitly on the multiple of P that we're taking. Okay, so by the theorem of Fermat, around 1 on root log B, I mean, okay, it's a little more difficult than the theorem of Fermat, a little more interesting, but around 1 on root log B of integers with size B are sums of integer squares. So let's look at a slight variant of this counting problem. Instead of asking for the y coordinate to be a sum of 2 rational squares, let's ask for the e coordinate to be a sum of 2 integer squares. So this is a bigger set. If the y coordinate is a sum of 2 rational squares, that means the numerator and denominator here are sums of 2 integer squares. E cubed is a sum of 2 integer squares, and if and only if E is a sum of 2 integer squares. This is a bigger set. I'm counting more things. And now, if one does the same heuristic, if one guesses how large this set ought to be, well, 1 on square root of the logarithm of the size of E is something like 1 on n, 1 on little n. So the naive guess for how big this is about log of capital N. And I claim that this is actually a rather exotic answer for us analytic number theorists. So let me just clear out the discussion of why this quantity might be uniformly bounded. Right, exactly. So it's exotic because let's forget about multiples of a fixed point. Let's say that E has rank 1. Maybe we say it's rank 1 and torsion free, so that this is precisely the set of points. This is basically the set of rational points on the elliptic curve of height up to a given bound. If we say that all of the points on E are multiples of the point capital P. So in that case, okay, so here's the set again. This is the set of points on the elliptic curve of naive height up to capital B. I've written them in terms of integers solving this equation with GCD1. So in that case, the heuristic that I just wrote down translates into this here. So the number of rational points of height up to capital B on this elliptic curve, co-prime integers solving this equation. The heuristic translates into this is about log B. And this is what I'm calling exotic. So we see examples of varieties where the number of points of naive height up to B is a power of B. We see examples where it's a power of B times or divided by a power of log. We see examples where it's just a power of log. But this log is a little unusual. So the problem in this form has been discussed before. So Bjorn Poonen and Tim Browning asked about versions of this. And this actually is really quite, very little is really known here. We haven't really added that much compared to what you'd expect to be true. So it's actually, as far as we are aware, not even known whether I forgot to write here the condition that E is a sum of 2 squares, I realize. Okay, yes, so please imagine that here it says that the E coordinate has to be a sum of two squares. Otherwise, this doesn't make sense. Otherwise, this is just the count of rational points on the elliptic curve. Sorry about that. Okay, yes. So it should say that E is a sum of two squares in order for this to make sense. Let me go back to where it does say that. Right. So as far as we know, it's not even known whether there's an example of an elliptic curve such that this set is actually infinite, or an elliptic curve and a point such that this set is actually infinite. So it ought to grow very slowly with the height, and it's unclear whether it actually goes to infinity at all. We can find some sort of similar sets where you put some other polynomial in these coordinates instead of just E, and it's like a positive proportion of all points. The equation is soluble, but we can't. This nice formulation, we actually aren't sure whether this quantity is ever goes to infinity. So this result that it's little o of the trivial bound is a tiny ant-like step towards this rather mysterious problem. Okay. Right. Yes, so and our results actually all apply. So this, because we wanted to formulate them in a nice general way, this isn't totally clear in the paper, but our proof actually applies to the result formulated in this way as well, the problem formulated in this way as well. So if one looks at this E coordinate of multiples of a fixed point on an elliptic curve under these assumptions, we again get that 0% of them have this E coordinate be a sum of two squares. Okay. And this is actually the method of proof. I said, so I'll come back to this, but as I said, this is a bigger set than the one we had before, and this is actually the result. This is how we prove it. Okay, but I'll explain that properly in a minute. Right, so I'm now going to remove this heuristic, and whenever I announce that I'm going to remove something, you're of course welcome to interrupt with questions about the thing I'm about to delete. All right, so so this slide will be coming back to a bunch of times. So this is sort of the very high-level sketch of the way this is proved. Because it's a high-level sketch, it currently makes no sense. Hopefully, by the end of the talk, this slide will make some sense. That's the goal. So here again is the result. Here is some notation, most of which we've seen before. So again, we've got a fixed point, fixed elliptic curve. We take multiples of the fixed point. We write that in terms of coprime numerators and denominators. Then I just want to observe something nice about this E coordinate, something about what it means, if you like. So a prime P dividing this E coordinate, this is the same as this point being congruent to the point at infinity mod P. So, and moreover, P to the K dividing E is the same as N times P reducing to the identity mod P to the K. So this is almost it's almost obvious. So yeah, this is kind of what one might naively expect, that if a high multiple of P divides the denominator here, this is saying that this thing reduces to the point at infinity modulo that power of. Okay. And in particular, this gives this E some sort of nice multiplicative properties. For example, if capital P reduces to the point at infinity modulo some prime, then so does any multiple of it. Since any multiple of the point of infinity is the point at infinity, which means that E1 divides all the ENs. E1, if p to the k divides E1, that means capital P is the point at infinity modulo p to the k, means any multiple of capital P is the point at infinity modulo p to the k. Okay, and we'll see some more facts like this soon. Okay, and this is the thing that I said before, that the headline statement has the y coordinate of n times p here, but the method of proof is essentially to show that this e coordinate is almost never the sum of two squares. So this inequality here implies this inequality here, because if the y coordinate is the sum of two rational squares, then the e coordinate, the cube root of the denominator of the y coordinate, is the sum of two integer squares. Right. Now, how do we prove this statement? Well, so we use the Selberg sieve, and we use these two results. And this one, which actually has the simpler statement, is sort of the crucial one. So this one has a statement which I'm about to explain. Basically, the statement of this one is messier, but the proof is neater. The statement of this one is neater, but the proof is quite technical. Okay, so this key proposition with the neat statement and the nasty proof, this says that, okay, again, we fix E and P, we're satisfying the assumptions of the theorem. So the real points of E are connected and P has infinite order. And the claim is that a positive proportion of primes L have EL on E1 congruent to 3 mod 4. So I've divided by E1, which I'm allowed to do by what I said just now. You know, one can imagine why this might be useful, because we want to show that EL isn't a sum of squares. So we want to find a prime power divisor of a maximal prime power divisor of EL, which is congruent to 3 mod 4. This seems like a reasonable thing to ask for. Okay, and here I've just written out what exactly I mean by a positive proportion of primes L have this. So if we look at just ordinary rational primes going up to some bound capital L, and we impose the condition that EL on E1 is 3 mod 4, then that's bounded below by a multiple of L on log L. So this is where the meat of the proof is. And the way that we use it, well, we use the Selberg sieve, like I say, and we also use this lemma here. And what's going on here is that this is going to allow us to kind of sieve out the primes L. So essentially what this is going to tell us is that if En is a sum of two squares, then none of these primes L can divide En. Okay, that's not quite what, there's technicality, but morally, in some sense, the sort of simplified false version of the proof is we're going to show that if En is a sum of two squares, then none of these primes L can divide N. This is a positive proportion of all primes, and that's going to force N to lie in a set that saves a power of log like this. Okay. So to state exactly correctly how that works, Vp is the p-valuation of an integer m. In other words, it's the exponent of the maximal power of p dividing m. So if L is a prime like this, then there's a prime congruent to 3 mod 4. So L and P there's going to be a bunch of interplay between these two different primes. So if L is one of these primes, then there's a P congruent to 3 mod 4, such that the p-valuation of this number is odd, because otherwise, if every maximal prime power divisor of this number were 1 mod 4, 2 mod 4, then, well, 0 mod 4, then this thing couldn't be true. Okay. So what we do is we say let's have L be prime, P be prime, and let's let P be one of these guys. So P is a prime congruent to 3 mod 4, such that the P valuation of this quotient is odd. And let's make this additional assumption that L doesn't divide E1. Okay. We kind of want to make sure that we're not dealing with something that just comes from E1. I mean, there are only finitely many L that divide E1, so this isn't going to be a problem. We'll come back to that. Okay. Then the dilemma says that whenever L divides N and P times L doesn't divide N, then the P valuation of En is odd. In particular, because P is congruent to 3 mod 4, this means that En isn't a sum of 2 integer squares. So this is what I mean when I say that we can sieve out these primes L. So this is going to tell us that, so somehow if this condition fails, if PL divides N, that turns out to be rare. One can show that there aren't very many L with PL, there aren't very many N with PL dividing N, and otherwise N can't be divisible by any of these L's. It's a positive proportion of L's, and that gives us this logarithmic saving. Okay. So as I say, this slide will come back to a bunch, and hopefully by the end of the talk, it's going to make more sense. Okay, so I have, there are 3 steps here, right? We've got to prove this proposition, we've got to prove this lemma, and we've got to apply the Selberg sieve to prove the theorem. And I kind of intended to solicit opinions at this point. So I don't know if anybody has any preferences about which you want me to do most. I'm not quite sure how this works for people in the other room. I don't know. Presumably they have do they have a way of communicating questions? Can we see them? Yeah, all right. Yes, that's a good question. Okay, the question is, can I repeat the options? There are 3 steps remaining. Prove this proposition, prove this lemma, and use the Selberg sieve to prove this estimate here. And kind of what I want to focus on is the proof of this proposition. That's I think the most interesting part. But I also, so I think what I'm going to do, unless somebody's immediately curious about one of the other steps, is I'm going to talk about the proof of this proposition, and we can, if anybody's curious, we can, or if we have time at the end, then we'll talk about the other 2 steps. But like I said, okay, what I will say briefly is that this business with the Selberg sieve is more or less what I hand-wavily said, that using this lemma, it's sort of more or less true that none of these primes L can divide N if E is a sum of 2 squares. So we can sieve out all of the N's that are divisible by such an L, and that gives us this bound. The lemma, so I put a very minimal, concise proof of this lemma on the slides. This follows from Hensel's lemma. That's morally what's going on here. This Hensel's lemma is telling us that the p-evaluation of En is going to be the same as the p-evaluation of El, provided that these conditions are satisfied. Okay, so I mean, I fear that this isn't going to be on screen long enough for anyone to understand it, but as I say, you're welcome to ask questions about it, or we can come back to it later. Or you can go and look at it at tiny.cc/greentent. Okay. So as I say, what I want to do is I want to talk about the fun part, the proof of this proposition. So the proof of this proposition uses elliptic sequences, or elliptic divisibility sequences. So I'm not going to define what an elliptic sequence is or what an elliptic divisibility sequence is. And the reason I'm not going to do this is that different authors use the terms differently. And I don't want to either lay down the law or go through an exhaustive explanation of how everyone's used it. But the general idea, morally, what an elliptic sequence is it's something which looks like En. So En itself, this sequence of denominators, might or might not be an elliptic sequence depending on your definition and your elliptic curve. But morally, what an elliptic sequence is it's something which looks a bit like this sequence of denominators. And there are various particular definitions of useful sequences, useful classes of sequence which look like En. Okay, so in particular, what we want to do is we want to understand En mod 4. We want to prove this proposition, which says, well, really En on E1 mod 4, I suppose. We want to prove this proposition finding lots of primes L such that EL on E1 is congruent to -1 mod 4. And elliptic sequences are these things which look a bit like En and have nice properties when you reduce them modulo a fixed modulus. And that's why we're using them. So here again is the Weierstrass equation. Okay, and to define the particular type of elliptic sequence that we're going to use, I need to introduce division polynomials. So these are the polynomials associated to the multiplication by n map on the elliptic curve. Okay, there we go. I've said what they are. Immediately delete this. Move on to the next slide. Okay, no. No, this is what I mean. Okay, yes, no. Okay, so this is a good question. The question is, what's going on with this notation, basically? What's going on with this so-called non-singular part? So let me explain. So in order to define the type of elliptic sequence that we're going to use, I need to define these division polynomials. And in order to define the division polynomials, I'm going to relax some assumptions for a moment. So I still have this Weierstrass equation, but just for a moment, I'm not going to require that this define an elliptic curve. Just for a moment, in order to define the division polynomials, I'm going to say, no, this is just a Weierstrass equation. It can be singular. It's just a Weierstrass equation defining a cubic curve. And the coefficients are just some rational numbers. For a moment, they're allowed to be rational. They don't have to be integral. So this now cuts out some cubic curve in P2. And okay, so it might have a singularity, but its non-singular points, these are still a group in the usual way. And this group has a multiplication by n map, and that's some rational map on that's given by some rational map on this cubic curve E. So I mean, if you want to, you can think about this as being an elliptic curve. The point is that, I mean, strictly speaking, to define these things, it makes sense to relax these assumptions and say, well, actually, this still works even in the degenerate case. Okay, we have the multiplication by n map on the cubic curve given by this equation here. Okay, so here there are some polynomials in the ring of polynomials on this curve, on the zero locus of this polynomial, which define this rational map. And okay, so the numerators here, they're just some polynomials. I mean, I wrote them like this because I can. The numerators here are just some polynomials. The important thing is that there's these polynomials have integer coefficients in x, y, and a. So x and y are the coordinates of the point that we're multiplying by n, and a are the coefficients of the equation defining the curve. So this is something with integer coefficients in these variables in the ring of polynomials on this curve f equals 0, and in particular psi n squared and 4y psi n cubed are these are the denominator. These are the denominators of this n times the point x, y. And these look a little bit like, these denominators look a little bit like this E that we saw before, since there's a square here and a cube here. So that's a bit suggestive. Okay. And these polynomials that give us the multiplication by nmap, they satisfy this recurrence relation. So really the crucial facts here are that these polynomials have this square and this cube on the denominator, and they satisfy this recurrence relation. And this is the key thing which enables us to understand the reduction mod 4 of this sequence of denominators En. Because this recurrence relation tells us what happens modulo 4. If you take a sequence modulo 4 satisfying this recurrence relation, this gives us very strong information about that sequence mod 4. So that's very hand-wavy. We'll come back to that soon. Okay. So people are usually pretty sloppy and don't distinguish between what people, including me, are usually pretty sloppy and don't distinguish between what I'm calling capital psi and lowercase psi. So this is, strictly speaking, a polynomial in the ring of polynomials on this cubic curve. And it has a canonical representative, which I'm calling capital psi, which is really a polynomial with integer coefficients in x, y, and a. And what this is we set some initial conditions. We set the first 4 psi n's. And then we use this recurrence to calculate all the others. So just to be clear what I mean here, I mean these are by definition the polynomials psi1, psi2, psi3, psi4. They're polynomials in x, y, and a. Well, psi1 and psi2 are polynomials in x, y, and a. Psi3 and psi4 have these b's in. These b's are some known polynomials in the a's. I didn't want to fill up the slide by writing them out. Okay. And the point is that once one knows the first 4 polynomials, if one asks that the polynomials satisfy this recurrence, it turns out that this uniquely specifies a whole sequence psi n of integer polynomials in these variables. Okay, so let me make a little room so that I can be even clearer about what that means. I'm just going to remove the statement of the proposition. It'll be back in a while. Okay. Right. So we've got these 4 polynomials in integer coefficients in the coordinates of a point on the curve and in the coefficients of the curve, and they satisfy this recurrence relation. So if you put capital psi instead of lowercase psi, this is still true. And what happens is that this sequence En from before, so if we let P be given by xy, so that xy become fixed rational numbers, and E be a fixed elliptic curve, so that the A become fixed rational numbers, or fixed integers if we ask that it have integer Weierstrass equation, then, okay, if things are suitably nice, if P has good reduction and the Weierstrass equation is integral, then this En is very closely related to the value of this polynomial psi n. So, yeah, under propitious circumstances, these things are actually the same. In general, they're very closely related. And because this psi n satisfies a recurrence relation, it has good behavior modulo, for example, 4. So we aren't in this situation where these things are equal, but we are in the situation where they're closely related. We're going to see exactly the form of that we're going to use in a moment. So this thing, this E1 to the n squared psi n, this is an example of something which is commonly called an elliptic divisibility sequence. So this sort of thing, this sort of object was, I think, first studied by Ward. And there are some sort of key names in classifying and describing these sequences and relating them to points on the elliptic curve. Yep. Right. So the question is, what does it mean P has everywhere good reduction? Okay, so what I mean is that we have an integral via stress equation, so we have uniquely defined reduction mod P maps. If P is a prime of bad reduction, then the reduction mod P might have some singular points. The reduction of this equation might define a singular cubic curve. And P has bad reduction at a prime if it reduces to a singular point on the reduction mod P of the elliptic curve. And P has everywhere good reduction if it doesn't reduce to a singular point at any prime. So that's what P has everywhere good reduction means. Okay. So yes, the initial interest was kind of in classifying these sequences, and then later, especially Shipsey and Stange related them to elliptic curves in various ways, actually for cryptographic purposes. So this is applications right here. Okay. So I'm unfortunately going to clear out these great names in order to make a little room to explain what happens in our proof, and also the definition of the division polynomials. Okay, so here is the division polynomial recurrence relation. Okay, so for all integers here, this identity holds for these integer polynomials. Okay. So here again, we let our point P have coordinates x and y. We assume it has infinite order. We assume, so I guess I haven't explicitly said this, but I'm now assuming once again that oh no, I have said it, okay. I'm now assuming once again that this Weierstrass equation is integral. So that we have this nice description of n times p. Okay, and what we actually use is a recent result of Vatsobia, which says that this quotient En by E1 actually satisfies a very similar recurrence relation to this one for capital psi. So this uses the whole theory of elliptic divisibility sequences, or large parts of it in the proof, even though sort of once we've got this result, we can kind of use the whole idea of division polynomials and elliptic divisibility sequences as a bit of a black box. Okay, so what is this similar recurrence? So what we've got to do is we've got to take this En on E1 and we've got to put a sign on it. So once we've fixed the point xy and we've fixed the a, so we've fixed the elliptic curve, then this psi n is just a sequence of integers, or just a sequence of rational numbers, I guess. So these don't have to be positive. So we've normalized the e's so that they're always positive. But these psi's, they don't have to be positive. And in fact, that turns out to be crucial for them satisfying this recurrence relation. So what we do is we take the quotient En by E1, which is some integer, and we attach a sign to it, which is the same as the sign of psi n. Psi n is now some rational number, sequence of rational numbers, and we put the same sign that psi n has on the quotient En by E1, and we call this beta n. And then, under some assumptions that I'll explain, the same recurrence relation that holds for psi holds for beta. This is just the denominators of points on the elliptic curve with some signs, and they satisfy this recurrence relation if we choose the signs correctly. Okay, so there's an assumption here, which is that this n and m and r that appear in this recurrence relation, at least two of them have to be, they're all allowed to be any integers except that at least two of them have to be multiples of a certain quantity, capital M. I mean, the way I've written it, any two can be multiples, but this thing is symmetric enough that it's equivalent, but yes. So at least two of them have to be multiples of this capital M. What is capital M? capital M is the smallest natural number such that M times P has everywhere good reduction. So Alex helpfully made me define this before. So because we have an integral via stress equation, now we have reduction mod P maps. So M is minimal such that M times P doesn't reduce to a singular point on any of the reductions mod P. And so this is well defined. I mean, that's a fact. A slightly non-trivial fact that this is a well-defined thing. Oh yeah. So we liked. Yeah. I guess we really liked the generality, but maybe we should have flagged it up more. Okay. Yeah. This condition, it's nothing. Don't worry about it. Thank you very much. Okay. Yeah. So the point that Alex is making, for those in the other room, is that this capital N is often 2. So this is actually a pretty mild condition. Okay. And in particular, this implies that the sequence beta n mod 4 is periodic. So I'm not going to prove that. Actually, this implies that for any modulus q, the sequence beta n mod q is periodic. That's maybe a tricky exercise, but I guess if you want to show that this implies that beta n mod 4 is periodic, you could I guess just try all of the possible sequences mod 4 and convince yourself that if they satisfy this recurrence relation, they have to be periodic. After all, there's only 4 integers mod 4. Okay. So I'm just going to make some room by removing the Weierstrass equation and the recurrence relation for the division polynomials. Okay. So in order to prove our proposition, which is about this quotient En on E1 mod 4, we need to know what these signs are that we've just affixed. So these are given by a theorem of Silverman and Stevens. So sigma here is some mysterious sign. It's plus or minus 1. So sign here is plus 1 if this thing's positive, minus 1 if it's negative. And this thing is the floor function, so the greatest integer, which is at most this thing. And okay, the result is that for some irrational number, which actually they explicitly construct this irrational number. Okay, for some irrational number, which depends on E, the curve, and the point, this sign is given by well, it's basically given by the parity of the integer part of n times alpha. So if, in particular, if P is in the connected component of the identity, then the sign is so sigma also depends on E and P, right? Sign is sigma to the n minus 1 times minus 1 to the integer part of n times alpha. So it depends on whether n is even or odd and whether the integer part of n times alpha is even or odd. And there's also this needs to be slightly modified if P isn't in the connected component of the identity. And this is why the theorem I stated at the start had this hypothesis that the ER be connected. I mean, we can relax that under various conditions, but it's sort of the simplest sufficient condition for our methods to work. Okay, so because I'm assuming that E of R is connected, we're always in this first case. The sign that we've affixed is always given by the parity of the integer part of n times alpha, so for some irrational alpha. Okay, now I'm going to keep the definition of beta n, I believe, but I'm going to suppress this recurrence relation of Sobio and keep the fact that it's periodic. Okay, so here's the proposition that we want to prove again, and here's what I was saying before. Let the period of beta n mod 4 be rho, and let alpha be this thing from the first case of Silverman-Stevens. Because E of R is connected, we're in this first case. We introduce notation for the fractional part of a real number. So if we then ask for primes which are congruent to 1 mod 2 row, I mean, actually, row is often even, so I don't really need that, but okay. L is congruent to 1 mod 2 row, which means that beta L is congruent to 1 mod 4, because L is congruent to 1 mod row, so beta L is congruent to beta 1 mod 4, and beta 1 is, well, so psi 1 is 1. That's been erased from the board, but psi 1 is 1. So the sign that we're attaching to beta 1 is 1. So beta 1 is just E1 on E1, so beta 1 is 1. So if L is congruent to 1 mod rho, this means that beta L is congruent to beta 1 mod 4 by this periodicity. And so beta L is congruent to 1 mod 4. I've put this 2 here so that L would be odd, which means that sigma to the n minus 1 is 1. This is plus or minus 1. Okay. So if we impose this condition on the prime, perfectly innocent condition, lots of primes satisfying this condition, then beta L is congruent to 1 mod 4. So now what I need is EL on E1 congruent to minus 1 mod 4. So I need the sign attached to beta L to be minus 1. And that will be true if the parity of the integer part of L alpha is odd. In other words, if this fractional part is between a half and 1. Okay. And there are lots of primes satisfying these conditions. So this is just Dirichlet's theorem, primes in arithmetic progression, and using, for example, Weil's criterion, one can get lots of primes in a positive proportion of primes in an arithmetic progression, also in this kind of irrational arithmetic progression. Okay, so this is like saying that the fractional parts of, if we let L range over primes in this arithmetic progression, then this fractional part is equidistributed in the interval 0, 1, which is true. Okay. Okay. So that's the sketch proof of this key proposition. Sigma to the, yes, thank you. This should be an L. Yes, indeed. Okay, so that's the sketch proof of the key proposition. As I intuited, that was about what I had time for. And yes, so I'll just recall that the idea is that this gets inserted into the Selberg sieve to get rid of, I'll just put it on screen so I have done. This gets inserted into the Selberg sieve. We sieve out the collection of primes satisfying these conditions, satisfying EL on E1 is 3 mod 4. And yes, this ends up being, there's a term coming from this relatively harmless lemma, and then there's this term that I've been talking about, where n isn't divisible by any of these L's. And this, okay. And this gets dealt with by the Selberg sieve, and the other gets dealt with by relatively, there is one non-trivial fact that is used that I haven't told you about, which is that the prime P appearing in this lemma has to be somewhat large. This is true because of the number of points on an elliptic curve over a finite field. But okay, I have not left adequate time to explain this. So I will just flag up that there is precisely one really non-trivial fact left that I hadn't explained. Okay. Yeah. Yeah, that's true. Yeah. You make a good point. Yeah, there's a version of our main theorem with instead of I mean, this is basically some kind of Brauer thing, right? Yeah, no. They didn't make it in. They made it into the title, but not into the slides. So the question is that there were Brauer classes in the title, and indeed the Brauer classes didn't make it into the slides. So the point is that there is a more general statement of our theorem involving Brauer group elements, which allows us, for example, to put a somewhat more general field norm here than just sum of two squares. Not an arbitrary field norm, but a somewhat more general thing here than a sum of two squares, for example. So these methods are flexible enough that one can do more with them than just sum of two squares. And that's why it says Brauer in the title. The paper's on the archive. I didn't put it in the slides, and I'm not going to attempt to explain it verbally.
Know anything about this little omega actually?
That's a very good question. So the question is, what do we know about rho, and is the omega up here explicit? So let me go back to where rho actually appears. Let's see. Yeah, here we go. Okay. So the point here is something what is obvious to Tim, and therefore he skips over without saying, is that the saving. Let's get this right. Okay, so this omega appearing in the theorem, the power of a log that we save in the theorem, this is intimately connected to this period rho of beta n mod 4. And in particular, in order to make this omega explicit, we need to make we need an explicit bound for this period rho in terms of E and P. And the answer is basically yes. We do have an explicit bound for rho that is in there somewhere. I think our bound is probably a bit crude. It's often smaller than our bound. And we didn't think very much about sort of the statistics of how large this period usually is. But yes, the omega that we get is explicit, and in order to do that, we get an explicit bound for rho. Sure. Let me put that up again. So the point is that we have this lemma, which I claim is basically Hansel's lemma, which says that if we have a prime L such that EL on E1 is 3 mod 4, and L doesn't divide E1, and L divides N, but this P times L doesn't divide N, then En isn't sum of two squares. So here I've chosen for each L, I've chosen a PL. So in order to do the sieving step, for each L, I've fixed a prime PL congruent to 3 mod 4, such that the P valuation of EL on E1 is odd. The point is that we have in our bound for the number of ENs that are sums of two squares, we have an error term which is all of those N's which are divisible by PL times L for some L in our sort of sieving range. And the point is that this PL actually has to be bounded below by a multiple of N of L, which means that the proportion of N's which are divisible by PL times L is at most 1 on L squared, more or less. which means that actually this, if we choose the sieving range correctly, this set is small. And the reason that these p's have to be large compared to these l's is that because why is this? So I guess so it is true that p doesn't reduce to the point p doesn't reduce to the point at infinity mod little p. I have not really explained here why that's true, but we can in fact assume that. And L times p does reduce to the point at infinity mod little p, because this p valuation is odd, and so this means that p has to divide EL, which means that L times p reduces to the point at infinity mod p. And what this means is that L is the order of the point p in the reduction of the elliptic curve modulo little p, which means that L has to divide the order of E of fp. And that is, okay, that's big O of p. So yes, there's a little twiddle at the end that I've suppressed, but